Graphing motion, part 1, interpreting motion graphs. This is a summary. Now our motion graphs are placed on the Cartesian coordinate system, and we find for our purposes we'll be sticking to quadrant 1. Time always on the x-axis. There's a lot you can do with quadrant 4, of course, but we're going to stick with quadrant 1. So our displacement time graphs, sometimes called position time graphs, maybe a distance time graph. For short, a DT graph. This is what we're working with. Again, time always on the x-axis. In this case, slope will equal velocity. Important thing to remember, slope will equal velocity on our DT graph. So here's a DT graph for a stationary object. Now I'm not going to worry too much about the numbers for this particular lesson here, okay? That's another whole thing altogether. The general shape of the graph tells us so much. Here, for example, horizontal line on a DT graph, the object is stationary. Where if it's moving at constant velocity, you'll see a diagonal line. Nice straight diagonal line. If it's accelerating, then you see it curve. An accelerating object will produce a curve on a DT graph. For velocity time graph, here slope is something different. Slope equals acceleration. Area can also tell us something now. It gives us displacement. So our velocity time graphs are VT graphs for short. Now for a stationary object, constant velocity object, or object moving acceleration, just like before, but this time the shapes are different. For stationary, it's a horizontal line on the zero, right on the zero, right along the x-axis. For constant velocity, it'll again be a horizontal line, but raised above the zero. For acceleration, this time it's a diagonal line. So the general shape of the line can tell us so much about the motion of the object. Now to keep all this straight, I'm going to use a little memory aid. Notice the D, the V, the A? Yeah, right here. The D, the V, the A. DT graph, VT graph, AT graph. A little shorthand for this. Let's see how this memory device works here. Well, notice a slope, the word slope and an arrow to the right. That means for a DT graph, the slope will give you velocity. Where for a VT graph, the slope, arrow to the right, gives you acceleration. It works backwards too. So here I have an arrow to the left, and that arrow is labeled area. So for an acceleration time graph, arrow to the left, you will get velocity. Actually get change in velocity, but close. For a VT graph, the area under the graph will give you a D, a displacement. Now how about velocity time graphs? Okay, well there's a velocity time graph. We've already looked at velocity time graphs, but a bit more here. This time, the area. So the area between the graph and the x-axis is displacement. That's what's happening there. So slope equals acceleration, area equals displacement. In a way, I don't really have to remember that too much because my memory aid will help me. So for a VT graph, there's a VT graph. Slope gives us acceleration, that's the movement to the right. For a VT graph, the area gives us D, displacement. So I don't have to remember this. My memory aid helps me. See what's happening in this example. Use the VT graphs below, which shows the smallest change in position. In other words, the smallest displacement. Well, again, I bring up my memory aid, and I'm starting with a VT graph, and I've been asked about displacement. Oh, that's a movement to the left. So area is what I'm looking for. So displacement equals the area. It's asking about displacement, but I'm going to think area. So which of these four graphs would have the smallest area? Well, certainly not that one. That's a huge area. This one's a pretty big area too. This one looks much smaller than this one. So I think that B is definitely the smallest area, therefore the smallest displacement. So again, what the question asks for, and what I'm thinking about, in a way, is two different things. It asks for displacement, but as I analyze the graphs, I think about the area, using my little DVA memory aid there. Here's another example. Let's see how this is working. In which section of the velocity time graph below is the acceleration most negative? Most negative. Well, it's a VT graph, okay? And we're asked about acceleration. Oh, well, that's moving to the right, of course. So in other words, we're talking slope here. So it asks about acceleration, but I think slope. So the most negative. Well, the most negative is going to be a downhill slope. So that narrows it down to an or a B. And the most negative is going to be the steepest one. So that would be. Yes, because acceleration equals slope. So here we have B. That's the correct answer. So once again, what the question is asking for and what I think about as I analyze the graph is a different thing. It asks for acceleration, I think about slope. My DVA memory aid helps me with that. Here's another example. A speed time graph, VT graph, shown below. The slope of the graph is blank and the area is blank. Aha, well, how do I remember this? Is it just straight memory? No, I've got a little memory aid to help me. My DVA memory aid. So, what have we got going on? The slope. Okay, it's a VT graph. They give us a VT graph, and that's about slope. Oh, that's going to be acceleration. Okay, so in other words, well, let's look at the first column. It asks for slope, and we realize it's not velocity, it's got to be acceleration, so it's either A or B, one of these two. So I just get rid of those two right away. Now I come to here, the area is, so a VT graph, and area, arrow to the left, is a D. So area equals distance, or displacement, you say. So in other words, it's not that one right there. There's only one remaining, of course. Process of elimination, I get my answer. Again, what the question asks for and what I think about in a way are two different things. My memory aid helps me keep track of that.